pick the physics of interstellar if you'd like. Okay, I'm on here, I'm recording. We're at 2, 4, 6, 8, 10. People are showing up or not. Okay, so we were gonna have an Astrobytes today, but that's been pushed off. Do you have an Astrobytes article for Friday?
Not yet.
Okay, let me know. That would be nice today. Exam. I have reviewed the material and including the next homework assignment and have realized that the next homework assignment is not part of exam 1. So we've already done all the homework assignment for exam 1. There may be, and we're going to be ending today the material that's going to be covered on exam 1, even though some of it doesn't have much of a homework or calculations or much at all. It's sort of conceptual stuff. Classification stuff is, all the stuff we've covered so far is stuff we'll cover in the first 5 minutes today is, and then we'll move on to other stuff. Results of the survey, at least 3 people did not pick either one of the night exam options. So we're in class next Wednesday. I could push it off, but we're already a week past where the material ends. To push it 2 weeks past, I would, moving it up would have been we could have had it this week probably if we'd wanted to. And I can't move it to Monday. I could move it to Friday next week, but it seems like it would be the same problem anyway, right? So 50-minute exam, come ready to go Wednesday during class. It'll be we're just commenting, exam next week will be in class Wednesday. There will be some, define this, there'll be some explain this, there'll be some calculate this, that kind of exam. Questions about logistics, Bailey?
Is it going to be an online thing or written?
It will be on paper written exam. You do not have Mathematica. You will have an equation sheet, which I will try to remember to post sometime before Friday. Other questions? Okay. APOD. Boom, there it is. Mount Etna, apparently the most active volcano in the on Earth. I did not know. It's not in the solar system. I'm used to saying Io is the most volcanic body in the solar system, and so when I say most volcanic, somehow I guess the solar system just pops right out at the end of that sentence without me even thinking about it. Mount Etna is the most active volcano, I guess, on Earth. I did not realize that. This is a picture of Mount Etna erupting. I guess it had a fairly violent and massive eruption recently that caused local flights to be canceled because they didn't want them flying through noxious, toxic fumes. But other than that, it's a starscape where you've got lots of stars, which are fun. And they think these are satellite and not like meteors and things. Interesting. You often wonder, it's easy to, these are difficult exposures to take. If you're a photographer, you've got both foreground, very bright objects and background, very faint objects. So often you should be skeptical whenever you see an image like this. Have they just taken an image and just put it on a random star field background? That happens more than you think it does for these kinds of things. This is not the same exposure. This is actually 2 images that are put together, but apparently was taken by the same camera in the same place at the same time, back to back. So one of them used the fairly short exposure to get the volcano and the eruption, and then a longer exposure to get the stars and the streaks in there. Although it can't be too long, because if you expose for too long, then the stars start moving and you get all the stars streaking. So you can place a limit on how long that exposure was just by how much or not the stars in the image are streaking. So there you go. Today's astronomy picture of the day. Oh, not only one of the most active volcanoes on. Oh, never mind.
The whole thing.
It's a lie. Oh, it is on the top of the list, though, isn't it?
We're continuously erupting for 3,500 years.
Emit the most lava. I guess there's different ways to do it.
I like that there's a volcano in Italy just named Stromboli.
Indeed. What is Vanuatu? I don't even know what that is. I'm going to click on it. A South Pacific Ocean nation made up of relatively 80 islands, roughly 80 islands. Oh. Scuba diving, coral reefs. Cool. I'm there. Let's go.
You learn something new every day.
I know. I didn't even know that was a thing. Wow. The internet, that's what the internet's for. Tell you stuff you didn't know before. Okay, let's just remind ourselves where we were. We were talking about absorption lines in stars and where they come from and why they're there and why they have the strengths that they do and why they have the shapes that they do. In fact, the shapes is what we're talking about right now. You can see this is an H alpha absorption spectrum. This is the H alpha line in a star, probably like the sun. This might even be the sun. I don't even remember. But you can see, obviously, this is a very. There's lots of lines going on here. Obviously, this is the most impressive one here, right at H alpha. But even around H alpha, there's lots of much smaller lines, and they all have different shapes, right? These are fairly Gaussian. I can't really see it, but these are fairly Gaussian and very narrow. This is extremely wide and not really all that Gaussian. This part kind of looks Gaussian, but it's got these very broad wings that are very non-Gaussian, actually. And we were talking about broadening mechanisms, and we were specifically talking about natural broadening. How far had I gotten on this? What had I written down?
I think just natural broadening.
Okay.
You talked about the
No, I had written down some
We
equations.
talked a little about Heisenberg. Yeah.
I had written this equation down, right?
Yeah.
And we know that E equals hc over lambda. So we can actually take this derivative. Did I take the derivative? I didn't take it. This is, I think, where we stopped. I did take the derivative. Del E del lambda equals negative hc over lambda squared. We can plug this in, and we get delta E equals hc over lambda squared times delta lambda. So we know that delta E, we also wrote down Heisenberg uncertainty principle, is about equal to h bar over delta t. So we can plug this in for this, and we get hc over lambda squared delta lambda is about equal to h bar over delta t. And that gives us, really, we're interested in delta lambda. What is the width of this thing going to be given this uncertainty? Just the straight up Heisenberg uncertainty principle. Delta lambda about equal to lambda squared over 2 pi c times 1 over delta t. So this is not a constant because the wavelength of these features will change, but this is the most important thing here. It's inversely proportional to how long, remember this delta t is, this is sort of a expected lifetime of that electron being at that state is. So a typical transition typically has two, a typical transition always has two, no, that's not true. Typical transition has two bound states, right? So there's some uncertainty in the energy of both of those bound states. And so In any transition, you've got two states, and this gives you delta lambda about equal to lambda squared over 2 pi c times 1 over delta ti plus 1 over delta t final. So if you've got an atom and it's sitting there, well, let's just draw this as an energy diagram. Energy n equals, we've got the ground state, n equals 2 state, right? An electron can be at any of these states, but what state it's in it will have some lifetime before it spontaneously moves out of that state. And so that will be the delta t that we're talking about. The longer that it's in that state, the larger this number is, and the smaller the uncertainty in the wavelength, and therefore the energy, and therefore the wavelength. The shorter these, the quicker the decay time, the more uncertain this is.
Are we adding or subtracting these 1 over delta t's?
You're adding them because you can't make an uncertainty any smaller than it already is. It's going to be some combination of those two uncertainties. You've got some uncertainty when this energy is, and some uncertainty when this energy is. They're only going to add together to give you more uncertainty when you're transitioning between them. What does delta t for the ground state? You have an atom here with the electron n equals 1 state. It's actually infinite. You won't spontaneously move out of the ground state. Atoms like to be, this is the lowest energy state. It's like you're not going to, if you have a ball at the bottom of the hill, it's not going to spontaneously move up to the top of the hill without somebody kicking it. So one of these, if you have a transition like at the Lyman lines, then one of these delta t's is infinity, and one of these terms go away, and it's only the uncertainty of the other one that matters. Okay, so this is a back of the envelope, calculation for how broad these lines should be, but it doesn't give you the details. It doesn't give you the shape of this line, and it turns out that this gives the rough width, but the shape is interesting, and it's not a Gaussian. Shape, the detailed shape is what's called the Lorentz profile. And guess what the Lorentz profile looks like? It's got a narrow core and a broad tailing, a broad extended wings. Kind of like that. Let's see. Oh, we mentioned equivalent width last time. Here is another way to visualize equivalent width that I tried to do before. This is how we measure the width of a line, or the area of a line. It is the area so the equivalent width of this line is, if this area and this area are exactly the same, then this is the equivalent width. Just going down to intensity equals 0. Some real spectra, I'll get back to that in a second. This, though, I think is a good representation. The red is a Gaussian curve, and the blue is a Lorentzian curve. So you can see the core is narrow, and these wings are much more important and broader, and extend out, much more important, much further away from the center. Okay, that's natural broadening. Doppler broadening.
Where are we getting the 2 delta t's again?
The 2 delta t's?
Mm-hmm.
So if this is a transition between n equals 3 and n equals 2 for H alpha, it's the time that it would be the lifetime of an electron here and the lifetime of an electron here.
Okay.
which sets the uncertainty on what this energy actually is and the uncertainty on what this energy actually is to give you the uncertainty in the delta energy between.
So we would need like the mean like plus on the decay lifetime. The mean lifetime.
Yeah, the mean lifetime of that state, right? How long in the atmosphere, in the environment that it's in, is it gonna typically last there? Yep.
Is that also being something we'd be given if we were asked to calculate that?
Yes. Yes. And I'm not sure we'll even do any calculations on this. This is kind of a, why do spectra look the way they look? Well, this is one of the reasons. And it's got some quantum mechanics in it, which is one. Okay, so we talked about natural broadening. Doppler broadening is another one that we mentioned last time. We mentioned one kind of Doppler broadening. I'm going to start with a different kind of Doppler broadening to start. We talked about the bulk rotation of a star, right? Some of it's being blue shifted, moving towards you, some of it's being red shifted. That should, for every one of these lines, broaden them out. But even if a star weren't rotating, you'd see Doppler broadening as well, just because of the temperature of the gas and the plasma that makes it up. So even when you're looking at the surface of the sun, and it isn't, well, it is rotating, but it's rotating really slowly. At the center, some of those particles are moving towards you, some of those hydrogen atoms are moving towards you, some of those hydrogen atoms are moving away from you, even at the surface of the sun, just due to the thermal motions of the gas and the plasma that's there. So atoms are moving due to thermal motion. You might remember the Maxwell-Boltzmann distribution. We talked about this in this class a little bit, and in Analyte 3, the Maxwell-Boltzmann distribution tells you for a gas of a certain temperature made up of particles of a certain mass, what the distribution of speeds of those particles are going to be. That is the Maxwell-Boltzmann distribution. So again, right. So if you, it looks like this, you might remember, this is speed as a function, this is number as a function of speed. And the most probable, this is the VMP, the most probable, the mode of this distribution, where it peaks, is about square root of 2kT over m, m being the mass of the particles in the soup. So just the back of the envelope stuff, delta lambda over lambda is VR over C. This is the Doppler shift equation. Lambda odds minus lambda rest over lambda rest equals radial velocity over C. And the radial velocity is all that matters because it's only the along the line of sight velocity that matters. So delta lambda for this particular case is, so we can plug this in and do some stuff. We get 2 lambda over C times the square root of 2kT over m as a rough width of how that's going to change those wavelengths. The factor of 2 comes because this is a speed, and some of those will be moving towards you and some of those are moving away from you. And so you have to sort of double you get double the width for a particular thing. Actual profile is about Gaussian. And the mass matters here, right? The smaller the mass of the atom, the larger this delta lambda is going to be. Hydrogen is moving a lot faster on the surface of the sun than iron is. And it's going to be Doppler broadened for this by the spike a lot more than iron is. Okay, cool. And finally, the first one we talked about, or mentioned last time, rotational broadening. Rotational broadening. This is the effect we talked about before. If a star is spinning, let's say this is the axis, it's coming around this way. So some of that is going to be, you can actually draw lines, and each of these lines is going to have the same radial velocity towards you or away from you if this thing is spinning perfectly edge on to you, right? So this side might be blue shifted. This side might be red shifted. And the further you get away from the center, the faster it's going to be moving towards you or away from you. And this part in the middle won't be moving at all, or it will be moving with the bulk speed of this thing towards you or away from you overall. And so this gives you a rotation profile, right? So you're going to see most of the light coming from this. That's going to be unred shifted or blue shifted. But some of this is going to be extremely blue shifted, and some of it's going to be a little bit. So you're going to get a curve that actually looks like this on a spectrum. This is the intensity versus wavelength scale. It's not. It's kind of like semicircular. It's not either a Lorentzian or a Gaussian. It's got its own weird kind of shape. But that comes just from the rotation. We can use this. In fact, I used it I've used it in my research to work backwards to measure stellar rotation. We're interested in how fast stars are rotating. We can take this. The same line should have all of these other stuff the same. And if there's vast differences between the widths of these lines from one star to the next, we know that has to be a rotation effect. And you can just look at these lines and tell how fast these stars are rotating. Question?
So, for one spectrum to get data from, like if we're looking at the sun, that has an appreciable width from where we're looking at it, and so where am I going?
Due to this, you mean?
Right, and so like for us to get like a difference in these in how much red or blue shifting there is all in the same image or all in the same data point, we must have a fairly wide aperture in that.
Right. So this is a good point. This is, if you just take an image of the sun or a spectrum of the sun with a nice instrument, you're probably not going to see this because you're looking at a very small port of the sun.
Right.
But every other star you look at, you're not being able to resolve that star. And so you're getting all the light at once. And so for every other star that you would look at besides the sun, you're going to see something like this. That's right. For the sun, it's going to be, if you happen to be looking at the redshifted side, the whole line's going to be redshifted, but it's not going to be broadened because you still see that single radial velocity. That's right. Here's an example of lines that are not of a slowly rotating star and a fast rotating star. This can make a huge difference in the widths of these lines and the depth of these lines, because this is useful. This rotation does not change the equivalent width of this line. And so you're just taking this area and squeezing it down into a broader thing, which is much less deep for the rotational thing. So this is actually a figure from my dissertation. You've got, I'm comparing, so I measured measuring lithium abundances in stars. I'll give you a research talk later in the semester. But I'm trying to convince the reader that the difference, so this is abundance of lithium, how much lithium there is as a function of temperature. And you can see there's real differences between these. And I'm trying to convince the reader that this is real, that this isn't just an error of, within the noise. So here are two spectra that I've overplotted on one another. And you can see this is a calcium line. This is a calcium line. This is an iron line. This is the lithium line. These, again, for the same temperature, all of these lines should line up. The only reason why this blue one has a deeper lithium line than the red one is because it has more lithium at its surface. So that is a way that we can just measure abundance differences for certain elements by looking at these lines. So that is, I hope you will see, if you can actually resolve this from where you're sitting, a plot that is not even close, right? These are much different, vastly different lithium ones, even though they look kind of close on this chart. Here's one that's even worse, even more of a sharp distinction between those two stars, and even a more. Now this is an interesting one because these two stars do not rotate at the same rate. Now, if you notice, this maybe you don't notice. This red one is a lot broader than the blue one was. You can't see the blue one as it was, but it was. In fact, this is much smoother because you can evolve this with a rotation spectrum, basically artificially rotate it up, and that's what I had to do to compare these, because obviously it's hard to compare stars that are rotating different rates and their equivalent widths. So I had to spin the blue one up to match this one so that we could see that these two lined up and this one clearly did not. So this is a real effect, and you can make use of it. It's actually useful for measuring things. So we're publishing a paper now that is how rotation is related to this lithium depletion and what that tells us about stars and things. So this is real. Right. And we've got Voigt profiles. I'm not even going to get into this. If you want to really measure lines correctly, you need to use a combination of a Lorentz and the Gaussian, and that's a Voigt, and how much there is of one or the other will change how the shape looks, but that's a detail that you don't really need to know. Curves of growth also. Okay, excellent. That is the end of chapter 9. That's really all I want to talk about chapter 9. Again, we'll come back and use some of the results from chapter 9 when they make sense in the context of what we're talking about. So,
at the end of the material.
it's also the end of the material for chapter 9, for test 1. That's right. Chapter 10 is the longest chapter in the book. We're going to spend the most time on it of any chapter in the book. It's the most important for understanding the stars. This is the theoretical underpinnings of how stars are structured on the inside, which is much less messy, it turns out, than the outside. It's still messy, but it's much less messy than the outside. In fact, you can write you can write down 4 differential equations that pretty much completely tell you what the structure of a star is. You solve them simultaneously. And that's our goal. Derive those stellar structure equations, and then see if we can, in certain circumstances, solve them in a crude way. That's our goal for this chapter, among others. Right. So, stars are fundamentally simple things. The exteriors, the atmospheres are messy, but they're fundamentally simple things. So our goal, which I basically already said, but I'll write down, develop a set of differential equations necessary and sufficient to describe necessary and sufficient to describe the physical parameters by physical parameters, I'm talking about things like density and pressure and temperature inside a star. As a function of radius and time. So these are going to be fairly simple models, as you would expect in an undergraduate astrophysics course, in the sense that they will be one-dimensional models. We're not going to consider any sort of rotation, which would force us to consider a second dimension. We're not going to consider any magnetic fields that have some non-uniformly radial properties. Everything that we're going to be talking about of these stars are going to be simple radial functions. Every parameter of a star is going to be the same as we move out. That's a pretty good approximation. The models that we'll get describe stars really well. Not perfectly, but really well. And so it's instructive to see how that process works and what those equations are and how we can use them to build models of stellar interiors. There are 4 of them, 4 equations. 2 of them are pretty simple. I'll get to at least one of them today, maybe even 2. And then it will take a lot longer to get the other. Equation 1, hydrostatic equilibrium. This is kind of familiar maybe from fluids even in analytic 3. We didn't really talk about this specifically, but we made use of it at some level. This is the fact that if you have a fluid, we can talk about the ocean, we can talk about the atmosphere, anything that is gravitationally bound to a surface and is not expanding or contracting, that gives us a very powerful constraint on what the pressure distribution in that fluid has. So this is the status in a fluid such that at all R, the net pressure on a shell is equal in magnitude to the opposite in direction to the self-gravity. So let me write that down and we'll talk about it. The net pressure force on a shell is equal to an opposite of the self-gravitation force. So think oceans. Why does the pressure have to go up as you go down in the oceans? Because each layer has to be supporting all the layers that come on top of it. If it weren't, it would have to compress or increase in pressure until it was. So the fact that the oceans aren't expanding and contracting says that they're in hydrostatic equilibrium everywhere. The fact that the sun isn't expanding and contracting says that it has to be in hydrostatic equilibrium. If this were not true at the shell of the sun, it would have to contract or expand. It means zero. Has to cancel out exactly. Okay. So we're going to model stars as one-dimensional spherical objects. We only need to worry about one spatial variable, and that's radius. So let's consider a shell in the star at radius r from the center. So here is the center of the star. This might be the outside here. But let's consider a shell. I didn't really draw that in the center. There we go. Let's consider a shell somewhere in the middle of the star, but not at the edge. So a shell of material. Let's define some things. M sub r, capital M sub r. This is the total mass inside the shell. Now, inside is going to become confusing. because I could mean two things by this. I could mean this mass inside the shell, or I could mean this mass inside the shell. I will try to make it clear which I'm talking about when I'm talking about them. In this case, I'm talking about all of this mass that is contained between r equals 0 and r equals the shell. So as I move out, this number is going to go up and up and up and up and up and up as I move to the center, to the surface of the star. When I get to the edge, m of r is going to equal m of the star. M of r, capital R, I'm usually going to denote to be the actual radius of that star is equal to m, the total mass of that star. Hopefully, if you're confused about this, this will give you a clue that I'm talking about all of the mass contained within the radius of that shell. Okay, let's call P the pressure at the inside edge of the shell. Let's let rho be the density, mass density within the shell. Now, within the shell, now I am talking about this region right here. That's the density there. The density is going to be changing as you go out, but if we make this shell small enough, we can make the approximation that that density is fairly constant within the shell itself. And because we're going to make this an infinitesimally small radius eventually, right? And we've already really done it. dP is the pressure difference across dr. So this is R, this is dr from one side to the other. And dP is the pressure difference from the inside to the outside of the shell. What are the units on dP? Right, newtons per square meter. It's a force per unit area, right? Force over area. So what is dP? What can we think about this as? The negative of dP is the magnitude of the net outward pressure force on the shell per unit area. Let me write that down and let's think about it. Right, we've got a pressure P pushing in all directions at the let's zoom in on the shell so we can actually see what's going on. We know that we have a net pressure P pushing in all directions on this surface. And we know that we have this is going to be P. This is going to be P plus dP on the outside. Oh. Right? So if that were, if the dP were positive, that would be the positive dP is the net pressure on this shell pushing it inward. The negative of dP is the net pressure pushing, inward. The negative of dP is the net pressure force outward. Per unit area, because pressure is a force per unit area. I'm getting lots of blank stares.
No, this was like question number 2 on our first fluids homework.
Excellent. Those not in fluids. Is this making any sense at all? Okay.
So the arrow pushing out, that wouldn't be P minus dP?
No, we defined P. We defined this P to be the pressure at the inside edge of the shell.
Right.
right? And P plus dP is therefore, pressure, dP is the pressure change across the shell. And so the pressure here is P, and the pressure here is P plus dP. Right, so if P were positive, that would be a net pressure inward. We know that that's not going to be the case. What is this pressure going to be doing? It's going to be holding up the star. We know that the net pressure has to be outward because the other force that's involved here is gravity pulling everything in. Right? So we know that dP is going to be negative. We know that the pressure is going to get getting smaller as we move out.
So P plus dP is actually smaller.
P plus dP is actually going to be smaller than P.
Why don't we just write it as P minus dP then?
Well, we could,
This feels more
because dP is negative. But dP is negative because dP really is negative. It is really decreasing as we move out.
Yeah, P is going to be a function of radius. So it
That's
makes
right.
sense to have-
And dP dr is going to be negative. And you don't want to change that definition of how things are moving as we move out. That's right. Okay. This must be, so this is, the negative of this is going to be the net outward force on the shell. That must be equal to the net inward force due to gravity per unit area for the hydrostatic equilibrium to work. Right? This must equal, what was the wrong one? I got something. The magnitude of the net inward force on the gravitational shell per unit area. Okay.
So any degree to which P is greater than P plus dP must be compensated for by gravity pull.
Exactly. Or you could think of it, this dP must offset any gravitational force on the shell. Right? That really is what's causing this dP to happen. Because there is a gravitational force on the shell pulling inward, there must be an equal force moving outward, and the only place for that to come from is a pressure gradient. You cannot have a self-gravitational thing without a pressure gradient and have it be static and self-supporting and no other forces involved. There has to be a pressure gradient.
This force law necessarily assumes non-turbulent, no mixing at all.
Yes, but even if gas is moving, this still has to be true.
Sure. Yeah. Because we're talking.
I mean, locally it won't be, right? If you have a blob moving up, then locally the pressure forces have exceeded the gravitational force. But there has to be another blob moving down, so that on average in that shell, this has to be the case still.
Sure.
Yeah. Okay. So what is the net force of gravity on that shell? Well, we know that the force of gravity is G times M1 times M2 divided by R squared. So this is just the normal Newtonian force of gravity equation, right? What are our two M's here? Well, we need M1 to be the mass of the total mass inside shell. And M2 to be the total mass of the shell. Now, if you've taken classical mechanics, you did a derivation where you probably showed that in considering the force of gravity of the shell, you can ignore everything outside of the radius if you have a spherical symmetric object, because it's perfectly canceled out. The gravitational force on this point for this shell depends only on the mass that's inside of the radius of that particular point. The mass of everything else cancels out. there's less mass over here, but it's closer. And so those things, and there's equal on top and bottom. Everything else, if you have a spherically symmetric distribution, the only thing you have to worry about when calculating the force of gravity is the stuff that's inside of that radius. This makes your life much easier. It means that we can ignore the entire rest of the star for this and make M1 just the mass inside the radius of that particular shell. So this is the force of gravity on that shell altogether. It's not the force of gravity per unit area, but we'll get there in a second. What is M2? So this is just MR, right? We've just defined what that is. That was one of our things we wrote up here. What is this thing? What's the total mass of the shell?
DM.
What?
DM.
DM, sure. In terms of things we've written down over there. Say it again?
M of R plus dr?
Yeah. How about in terms of the density? Rho
Times
rho times, yeah, you're going to need some V and times A, but we actually want this to be per unit area. So if I do something like rho dr, what is that going to be? That's going to give me, so this is a mass per unit volume. If I multiply that by a length, I get what? A mass per unit area, right? Rho dr is basically dm over A. And if I throw this in as it is, that's going to give me, instead of a total force, a force per unit area, which is exactly what I want over there. So F of G is equal to G times MR times rho dr over R squared. This is really over A. And this is the total inward force of gravity on the shell per unit area. I know that that has to be equal to dP, minus dP. And that gives me, if I bring the dr over here, a differential equation for the pressure gradient. And that is stellar structure equation number 1, the equation of hydrostatic equilibrium. Also known as the first stellar structure equation. Okay, the implications of this equation. The implications are this. It is the pressure gradient of a star. It is the pressure gradient of the ocean. It is the pressure gradient of the atmosphere that supports it. Without a pressure gradient, you have no delta force, and that what will happen to that layer if you have no pressure gradient? It will have to contract until a pressure gradient forms, and then it will stop contracting. It is that pressure gradient that actually supports that fluid on top. Yeah, pressure is not enough. You need a pressure gradient at all levels of the ocean and the atmosphere and stars to hold them up and make them not contract. Question?
So neither rho nor mass are going to climb like linearly with radius.
Right. That's a good point.
And then I imagine that's.
So this isn't the only equation we're going to need.
Right, so we're,
This has to be true everywhere. This is a necessary equation. It's not a sufficient equation to get where we're going. Oh, thanks. Cool. We're 2 lines away from the second stellar structure equation, but we'll do it Friday. It's exciting. Aren't you in pins and needles to know what the second stellar structure? I am too. Who knows what it's going to be? It could be anything.
Could just be a nice linear.
They're all different.
That's an easy one.
This is a pretty simple. The next one's pretty simple too, and then it gets way more complicated.
Are we going to have to solve the difference between 5 and 12?
Actually, that's not true.
Yeah.
There may be
It's like-
certain
that's like the
instances
first day.
where I ask you to solve these by half, but they'll be much simpler. I won't ask you to solve all 4 simultaneously.
Yeah.
They'll be simple. I will ask you to solve these. They'll be much simple. They'll be simple applications.
I don't remember.
Last problem.
That's okay. You can use Mathematica.
Tested it 3, but
I can do it every time.
And it'll be basically it'll come down to integral.
Oh, that's what you want.
oh, you teach that one.
That's exciting, Howard. Can I talk about test logistics for a second?
About what?
Test logistics.
Say that
For next week's test.
Test
Logistics.
1. Logistics.
Yes, sorry.
Certainly.
It's hard to enunciate with
Understood.
masks. I usually have a lab meeting at 2:30 on Wednesdays.
Do you want to start it early? Can you start early?
I think so. I haven't,
Okay.
yeah.
Let me
I have
know.
like an hour in between. Yeah, I'll keep you updated.
If you can't, we can work something else out.
Okay.
We'll just try to figure out a time.
Thank you.
They
Yeah,
give
that
you
should
extra.
be fine.
You get an extra 50%.
extra,
Okay,
yeah.
so that'll be extra 25 minutes.
Cool.
Okay.
Okay. Great.
Yep.
Yes. I was also wondering. I'm so sorry.
I don't think there's
but-
anybody in here beforehand, so you could just come in and start it, and
Yeah,
then
that's
everybody can
cool.
come in. If that works. If you want a separate space, we can make that work.
Maybe because like if people are like trickling in, then
That makes sense.
Yeah. I'm so sorry, but I was also wondering if I might be able to get a little more time on this one.
Sure.
This week has just been completely insane.
Understood. Friday?
Yes, that would be great. Thank
Okay,
you.
Sure. No problem.
Because yeah, it's tech week for the dance ensemble show, and I have
Oh,
like 3 papers due.
good Lord. MTV?
Dance ensemble.
Dance ensemble.
Yes.
Wow, I didn't know you were that.
Yeah, fun fact.
And you're doing a live performance with an
Yes.
audience?
It's actually free, so you should go if you want to.
When is it? This weekend?
Yeah, it's this weekend, Thursday through Sunday.
Wow. And it's
Yeah,
going to be safe?
Yes, it's socially distanced in the Alice Austin Theater,
Okay.
and like you can reserve your ticket on like the Geneseo ticket website, and it's only open to like senior Geneseo students and faculty.
Okay, cool.
Yeah.
Thanks. Maybe I will.
Nice. Yeah, it's just
Are you performing or just doing tech?
performing.
You're
Yeah.
performing. I didn't know you're a dancer.
Yeah, that's finer.
Cool.
It's really
Maybe I
fun.
did know that at one point. I've just forgotten.
Yeah. Well,
Excellent.
Thank you. I appreciate that a lot.
You're welcome. Yes, good luck.
Thank you.
Morgan.
I had the same thing, but I think I heard for.
Oh,
tests.
that's extension.
Yeah,
Yeah. How do you want to handle that?
just come before you so that everyone.
Yeah, does that work? Can you come
Yeah.
25 minutes beforehand?
Yeah.
Okay, you can either set up in here or we'll set you up somewhere else.
Okay.
And if you don't want people coming in, while
Yeah.
you're taking it.
Alright.
So, we can decide between now and then how you want to handle that. But,
Okay.
or if you know now, you can. let me know.
Also, I just want to see if I'm on the right track for the last question of homework.
Yeah.
I had like the main sequence
Yeah.
pretty clearly. Is there also supposed
Yeah.
to be like an under?
There's not supposed to be, but there is, and those. So, if you want some guidance on the last homework question, you should see, which is the plots. You should, for the first plot, you should see a nice main sequence, a little nice thing over here. There's going to be some crap down here. Those are probably fake stars. Those are probably not real. This is the very limit of the edge of what Gaia can detect, and sometimes some spurious things get in. So it's real in the data, but it's probably not real stars, because these are the faintest things you could possibly see, and it's just the boundary of what it's picking up as real and not real being a problem. So you can plot them. It's not wrong to plot them, but just know that you can ignore those things. They're probably not real things. Was that your question?
Yeah.
Yeah.
Thanks.
I was just wondering, for question 3 and 4 on the homework, how are we like supposed to go about doing that? Next 2 questions.
3 and 4.
Yeah, I'm pretty sure 4 they couldn't get it.
Let's see. Right. We kind of did. So you're going to need both the Boltzmann and Saha equation,
Okay.
right? And so, right, you want N2 over N tote.
For number 3.
So you're going to need Boltzmann for N equals 1, 2 to 1, and 3 to 2.
Okay.
And you're going to need Saha for H2 to H1.
Okay.
Right? And then the total number in H2, in N2 divided by the total is going to be the total number of stars, of atoms that are in the ground state and in the N equals 2 state and the N equals 3 state and ionized.
Is that like, was that going to be like number,
We did an example in class that was very similar to this. In fact, we basically did this example in class.
was that the one where you had each row do a different?
Exactly. We didn't, the difference is I only had you do N equals 1 and N equals 2. I'm asking you to N equals 3 now, but it's exactly the same thing.
So I forget the equation. I don't know if we went over the equation on the end of it. Like during.
Right. Well, that was, the end of it was N2 over N tote equals, right, N2 over N1 plus N2 plus N3 in the energy levels times the number in H1 divided by the number in H1 and H2. Right? So this is Boltzmann equation. These are Saha equations.
Okay.
And so you can divide both sides by N2, and then you're going to get a bunch of ratios down here, right?
Okay.
One of them is going to be N1 to N2, one is going to be N2 to N3, and then you can divide by N1 here, and then you're going to get the regular Boltzmann down here somewhere.
Okay.
This is going to be your final equation.
Okay. And that's for number 3.
That's for number 3. And number 4 is just using the same equation. This is going to be as a function of temperature, right? You're going to get a function that looks like this. So this fraction,
Yeah.
as a function of temperature, is going to look something like that.
Yeah.
Right? That's going to peak at about 10,000 Kelvin. Right? So the sun is like here. I ask you, how much lower is this than the peak? So it's just, once you define that, I assume you'll use Mathematica.
Yeah.
Once you define that function Mathematica, it's just plugging in 2 different values at different temperatures and taking a ratio of those values at different
Oh,
temperatures.
okay. Okay. All right. Thank you.
Yep.
I'll go last.
I just want to, sorry, quickly. The test is Wednesday in class, right?
The test is next Wednesday in class.
Okay.
Right.
Sounds good. That's all.
Okay. Yeah, there were at least 3 people who voted for neither of the evening options. So that's our only choice.
Can I just have you look at the Excel graph?
I can. I'd be happy.
Thanks so much.
I love looking at Excel graphs. It's one of my favorite things to do.
You saw the taking sarcasm.
I don't. It was real. HR diagrams, color mag. Are you kidding me? I love HR diagrams.
So I have the axes like correctly oriented and stuff. So like,
Yeah, you have a problem there.
yeah, that's what I figured.
You
And
have a
so
problem.
like last week I came in and asked you like just to define some stuff.
Right.
So obviously color, obviously apparent magnitude, right?
Right. So let's do.
These
I
are-
bet it's your absolute magnitude that's the problem.
And then the parallax.
Parallax
angle
is this is
It's
in milliarc seconds. That's right.
in millisecond seconds.
That's
Okay.
right. So the distance is that divided by 1,000. 1 over that divided by 1,000.
Yeah.
Yeah.
Okay. So
So this looks right.
I thought this was just an arc seconds. So
Oh.
that's partly where. Okay. Yeah. So that's
that could be it.
obviously simple.
But these numbers look right actually.
These guys.
Click on them. Hit escape. Click on this D again.
But this is a new sheet. I just
Oh, I
copied
see.
and pasted stuff. So I used this because it gave me
Oh, yeah,
I
that'll do
didn't
it.
realize they were in milliarc seconds.
Right. That could be your entire problem.
Yeah, and then absolute magnitude. like, because you use the
This should
little m
be-
minus big M.
That's right, equals 5
equals
log d
5 log
minus
d.
5.
Yeah,
That's
exactly.
right, so that should be right. So
Okay,
yeah,
it's just,
I bet you can change this formula and it we'll make it better almost immediately. But go ahead and try it. Change your distance formula to. It's basically 1,000 over that number, I think.
Yeah. That looks like it.
Okay, excellent.
But then I have to go and copy and paste a bunch of stuff and sort it.
Right, but you might be able to look at that graph immediately though. Oh, the graph is on the other sheet.
Yeah, it was on the other sheet, and I had
I did.
I was having
Okay.
issues, so I had to copy and paste only the values, so it's not going to transfer over.
I see.
All right, thank you.
You're welcome.
I'm
Do you know?
wondering just about the natural broadening. Why is that a special non-Gaussian?
Why is it non-Gaussian?
Yeah.
I don't know. That's a good question.
question.
That's a good question.
Because you said it's
Um,
steeper in the middle, right? So it's sharper and
That's right.
less uncertain than just a normal Gaussian.
In the middle, yes, but then more uncertain at the edges, right?
Oh, it stays. It looked like it was less certain at. Oh, yeah, you're right. So there's.
They have to be normalized. They're both normalized to 1, right?
Right.
The total area under that curve is 1. So, if you squish it up in the middle, you have to push it out somewhere else.
So this is. What's the x-axis here?
The x-axis is wavelength or energy, depending on how you want to look at this.
So there's.
But this is
So the Heisenberg uncertainty principle says that there has to be an uncertainty for any energy level. So could it be that like there has to be there has to be h bar over 2 for every possible wavelength. So the Gaussian approaches 0 as you go farther up. So Lorentzian has to approach.
it'll also approach 0. It'll just approach it slower. It just has a broader wing.
Yeah, maybe I'll Google Lorentzian and see if like Wikipedia has some explanation for why
Yeah,
that I
they
can tie
might.
into this.
They might. I honestly don't know.
All right.
If you find out something, let me know.
Yeah, sure. I'm glad to.